Now that we know how to plot Bode diagrams for any plant, we can study some additional conclusions about step responses. Consider a transfer function given by this, where both a0 and b0 are different from 0. That is to say, this function has neither poles at the origin nor zeros at the origin. We know from the final value theorem that the unit step response of this transfer function is given by b0 divided by a0. If the input to this transfer function is a step with an amplitude which is not 1, then the steady state output of this transfer function for a step with an amplitude k will be k multiplied by b0 divided by a0. This is what we call the gain of the transfer function. Now let us think about what happens in the Bode diagram of G of S at low frequencies. What we are plotting in the Bode diagram is the absolute value and the phase of this. At low frequencies, when omega is nearly 0, all these terms become irrelevant, and so do all these. So we will end up again with b0 divided by a0. What we will see at low frequencies in the Bode diagram is a gain of 20 times the logarithm of base 10 of b0 divided by a0. It is this low frequency gain in the Bode diagram that corresponds to the gain of the plant, which is, remember, the steady state value of the unit step response of the transfer function. For a second result, it does not matter whether or not there are zeros or poles at the origin, but we will assume that this transfer function is strictly proper. That is to say, there are more poles than zeros. When a step response begins, we are talking about very small values of the time. If the time is very small, that is to say that the frequency is very large. If the frequency is very large, we can approximate the frequency response of this transfer function by the largest terms here in the denominator and the numerator. In other words, for time values that are very small, this transfer function will behave as if only these terms mattered. It will behave just like a transfer function given by s power n minus m in the denominator. This is the difference between the number of poles and the number of zeros. What is the consequence of this? Suppose that we have a transfer function that has a difference between the number of poles and the number of zeros equal to 1. The step response of such a transfer function will begin just as the step response of 1 over s begins. And how does the step response of 1 over s begin? It begins like this, with a discontinuity in the derivative of the output. the output is continuous, but then it behaves as a ramp when it begins. And it can go up, down, it doesn't matter if it oscillates or not. But the beginning will have a discontinuous derivative. Now suppose that we have another transfer function such that the difference between the number of poles and zeros is 2. It doesn't matter what the order of these polynomials is, as long as the difference between the number of poles and zeros is 2. In that case, the step response of this transfer function will begin just like the step response of 1 over s squared. And how does this step response begin? Remember that the step response of this is given by a parabola. So we will have an output that is continuous and has a continuous derivative here. If the difference between the number of zeros and poles is 3, we will have a step response beginning just like the step response of 1 over s to the cube. And in that case, we'll have not a parabola, which is a curve that evolves with the square of the time, but we will evolve with time like the time to the third power. So the curve will be continuous, the derivative will be continuous, and even the second derivative will be continuous. So it will be even smoother when it begins. But what if the difference between the number of zeros and poles is 0? In this case, the transfer function is no longer strictly proper. This transfer function will have a step response that begins just as the step response of a constant. That is to say, the step response of a gain. So the step response will be discontinuous. There will be a discontinuity. Now it can go do this or this or this. It doesn't matter, but not even the output signal itself will be continuous. A last result concerns the influence of poles and zeros in time responses of transfer functions. Consider, for instance, these two, which have the same polynomial in the denominator and consequently the same poles. We can expand them both into partial fraction expansions. You can calculate the numerators by yourself, but you will see that the results are these. Now we know that these terms with s plus 1 in the denominator will correspond to exponentials like this, while these with s plus 10 in the denominator will correspond to exponentials like this. This exponential converges to 0 much faster than this one. So in this case here, we can expect this pole, the one which is farther from the origin, the fastest pole, to have a fast influence so that the response will mostly be dominated by this pole here. In this case, the numerator is clearly larger on top of the fastest pole, while this pole, the one which is closer to the origin, is normally the dominant pole. Because this numerator is so large, our response will not be close to the response I would have if only this pole were present. This pole will not be dominant because the fastest pole, in this case, will be very important. We can see that by plotting on the complex plane the position of poles and zeros, not to the scale, but this will suffice to show that while in this case the 0 is at minus 5.5, so does not really cancel the effect of any pole. In this case here, the 0 is at minus 110 divided by 101. That is more or less minus 1.1. Very close to this pole here, the effect of which will suffer a strong perturbation because of the 0. Another way of understanding this is to take a look at the Bode diagram of the transfer function. Here it is, the Bode diagram of the first of these two transfer functions in blue. If the second pole at minus 10 did not exist, we would have this Bode diagram in red. The difference is only significant at really high frequencies, that is to say, for short periods of time. But the way how the phase and the gain behave around the first pole is practically the same. Now, when we look at the second transfer function, we see that we will have this Bode diagram in blue, which is very far from the Bode diagram in red that only concerns the first pole at minus 1. Take a closer look at this Bode diagram in blue. You can see that the result we have here in blue is quite close to what we would have with only that pole. The gain only starts going down significantly at 10 radians per second, and the phase changes mostly in the 2 decades around 10 radians per second. That is why the first of these two transfer functions has a response which is dominated by the pole at minus 1, as you can see from this comparison here. The second is much faster